My name is Stephan Kleber. I'm PhD candidate at Ulm University, and in joint work together with TU Darmstadt, we propose a new solution for one of the tasks of protocol reverse engineering. Our work is titled Network Message Field Type Clustering for Reverse Engineering of Unknown Binary Protocols. Protocol reverse engineering solves the problem that we want to understand undocumented network protocols for which no specification is available. This is especially tedious for binary protocols where the information is very tightly packed in the messages and there is no human readable content. Therefore, we focus our work on binary network protocols. Protocol reverse engineering can be conducted observing the endpoints and the execution of the endpoints via reverse engineering of the binary. This requires access to the execution environment itself and is not always possible. Alternatively, the communication between the endpoints can be recorded using Wireshark or TCP dump, for example, observed and statistically analyzed. This is called static traffic analysis, and this is possible even if the endpoints are not accessible. Therefore, we focus our work on static traffic analysis. This is useful in several applications of security. For example, if we need to understand malware communication, and especially if we want to uncover exfiltration of data from trusted environments. Alternatively, if we want to validate the security design of undocumented protocols, we need to first understand the protocols themselves. Or finally, if we want to uncover vulnerabilities that are in the implementation of the protocol, then we also need protocol reverse engineering as preliminary task. This has been recently used to reverse engineer the Apple Wireless Direct Link Protocol, the AWL protocol, which is a Wi-Fi based peer-to-peer protocol. And our collaborators from Secure Mobile Networking Lab could discover a number of zero-click exploits that subsequently were fixed by Apple. They also provide an open re-implementation called the Open Wireless Link. Protocol reverse engineering targets different parts of the specification of protocols. For example, message format inference determines the message formats or also approximate segments that resemble the fields. Message type identification yields the types of the messages that represent different protocol functions, and semantic deduction gives an understanding of the contents of the messages, for example, which data types the fields have. For message format inference and message type identification, decent methods exist in related work, and we focus our work on the semantic deduction and cluster field data types. We rely on an existing segmentation of the messages into sequences of bytes, which we call segments. And we extract features from those segments that in the end help us to deduce the semantics. To give an overview over our contributions, we cluster field data types without a finite set of rules. Related previous work has used specific rule sets to identify session IDs and addresses individually. And our method is more generic. It's a heuristic method that is only dependent on the relationship of the values, and it works regardless of the byte positions of the segments. Our method is fully automated since we configure parameters for the clustering, and we derived the basic insights for how to do this by empirical observation of known protocols. Our method then is a lightweight and efficient way to automate the whole process. Finally, we evaluate our approach and we can achieve an F-score of 0.92, which is a cluster quality measure that just has an optimum of 1. And we can achieve a coverage of 87% of all the message bytes that we can analyze. The process that we conduct starts with the heuristic message segmentation, yielding an approximation of the fields of the messages that we call segments. We calculate dissimilarities of those segments, derive the parameters we need for clustering automatically, and then use the similarity and parameter to cluster segments that we originally wanted to obtain to gain knowledge about the data types in the network trace. Heuristic message segmentation is necessary since we need to deal with the lack of the true protocol specification. We have no message format available, and therefore we must approximate the fields in those messages using heuristic segmenters. And those segments they yield are approximations of the fields in the unknown binary messages. Several approaches that yield segments are available. We identified as the most sophisticated ones NetSop, which uses sequence alignment, Nemesis, which is based on statistical hypothesis about the field appearances. This is work we ourselves published in 2018. And finally, continuous sequential pattern algorithm, which performs frequency analysis of byte strings. By each of those segmenters, we can obtain substrings of messages that approximate fields in those messages, which we can subsequently analyze. We use those segments to calculate dissimilarities for each pair of them. From the trace that we have analyzed, the segmenter yields for all messages substrings that resemble the fields in the messages. And for each of those segments, we now interpret their byte values as vectors. We use these vectors of byte values to calculate the Canberra dissimilarity and place the pairwise dissimilarity in a matrix. We use the Canberra dissimilarity because it's a gradual dissimilarity that solves the problem of comparing vectors of different sizes to each other. And this helps us to make a more fine-grained decision than just saying that a segment is equal or not to another one. We proposed the Canberra dissimilarity in our publication at Infocom 2020. Using the dissimilarities between the segments, we now can auto-configure the parameter for the clustering. The last two steps now are the main contributions of our work. During parameter auto-configuration, we use a basic concept we also used in the Infocom 2020 paper. The auto-configuration is similar to the clustering of the message types we do in the NEMERE approach in this publication. We derive the parameter values from the distribution of the dissimilarities in the matrix for the whole trace. In contrast to this earlier approach, we now use the needle algorithm on the empirical cumulative distribution function, the ECDF, to obtain a value for the cluster parameters. And the needle algorithm yields the knee point, which is the maximum difference in this ECDF that represents the dissimilarity distribution in the original matrix. We smooth the ECDF before we apply needle to it to make it more robust and reduce noise. And the knee point itself that needle yields is then used as the parameter for dbScan clustering. To cluster the segments on dissimilarities, we use dbScan algorithm. dbScan is the density-based spatial clustering of applications with noise. It's a density-based method that makes no assumptions about the shapes of the clusters. This is important so that we do not have to make any transformations of the feature space. And we do not need to give it a target number of clusters, which we might not know if we don't know how many data types of fields in the trace we should expect. And as we have seen, the parameters, especially the epsilon, is deducible from the trace, and we can automate the usage of the clustering therefore. Now we have obtained clusters of segments that represent fields throughout the messages of a trace. Looking, for example, at an illustration of 4 different message excerpts, we can see that it's difficult for a human to interpret those messages, even though there are markings about where segments and fields begin and end in those messages, and there are data types annotated by labels. The structure is not simple to be grasped by a human. If we now mark the segments according to their clusters they have been placed in by our approach with colors, we can observe that there are recurring values throughout the message, that there is structure, that there are repeated instances of features in those messages, and this helps us to identify record-like structures, p-lists, type-length values, structures, based on the recurring clustered data types that we can see by the markings. We have now completed the whole process, which is an automated procedure that uses one vector for each segment as a representation and calculates a pairwise Canberra dissimilarity from which we derive the clustering parameter epsilon for the DB-scan clustering. This yields the clusters of pseudo-field data types that we can analyze further. And this is based on the assumption that the Canberra dissimilarity can separate data types. To validate this assumption, we now project the relative dissimilarities in the dissimilarity matrix for a trace of the Apple Wireless Direct Link Protocol into a two-dimensional plane. And we also color each of the segments according to their true data types. We obtained the fields, the field borders, and the field types from ground truth that we extracted from Wireshark dissectors of this protocol. This spares us that we have to deal with heuristic segments, which may be inaccurate, and we can rely on the correct segmentation into correct field boundaries according to the specification of the protocol. We call this topology plot, and the absolute position within the topology plot of the segment that is represented by a dot is irrelevant, therefore we omit X labels. The relative distance, however, shows us that there is a density core for timestamps specifically, there's a density core for integers with little endian representation, and there's also density cores for characters and for other data types. So we can observe that the assumption that the Canberra dissimilarity can separate data types is true actually. To now confirm this validation quantitatively, we use the clustering approach that we propose with the ground truth in combination as I introduced for the topology plots. So we have the correct field boundaries and the final correct association with data types for the clustering results that we get. And we use the well-known clustering metrics, precision and recall, which have an optimum of 1. So the top right corner of the plot is the optimum value. And precision gives us information about how correct the clusters separate field types, as the recall gives us information about how complete the coverage of the trace is throughout all the segments in the trace. And we can see that for all protocols that we use for our evaluation, the precision is almost 1. Therefore, we have very accurate clusters. The recall, however, is spread lower, which means that we cannot provide clustering for all segments in that trace, but for those where we can, the results are very reliable. There's only one exception, which is the SMB protocol. And this is a very specific instance of one trace of the SMB protocol that I picked to show this limitation of our approach. And if we investigate why the results are low in terms of precision for this specific trace, we notice that there is one cluster that mingles together timestamps and signatures. Those specific data types in this instance do not exhibit enough difference, so the clustering algorithm mingles them together. And if we ignore simply this cluster, then the precision is again closely to 1. The recall drops because we omit some values, some segments in the evaluation. Those two similar values allow us to have no clear distinction between the data types, and this is very trace specific and an example for the limitation of our approach. This validation that we performed here is only possible for known protocols since we have ground truth available. For unknown protocols, we need heuristic segmenters. And one of those that I introduced is Nemesis, and I use this as an example. paper contains the values for other segmenters as well. And we see that the precision drops for several protocols, still is high in several cases, but the recall is rather low for most of the protocols. This is due to the inaccurate segmentation. It leads to the splitting of values at wrong positions in the messages, and therefore this prevents the recognition of the similarities that we require for the clustering. To summarize our evaluation, we can cluster field data types accurately, and our approach works as it is intended. However, the example of the one trace of SMB showed a limitation that complex message formats require a large amount of variability, but the occurrence of those instances are not very common. It's only coincidental for a single trace of the protocol, and therefore we can deduce that our approach is robust despite this one limitation we have. The quality of the results depends highly on the segmentation in case of the heuristic segmenters. We evaluated our approach using segments from NetSop, Nemesis, and CSP, and they differ for different protocols. While one excels for one protocol, it basically may fail for others. In those single cases, we have very low recall and only mediocre precision. However, still, the coverage is high on average for all of those segmenters with a heuristic segmentation. We can yield 87% of the message bytes that have been correctly clustered on average throughout the message traces. When we compare this to related work and we identified Field Hunter as being the state of the art, it has been introduced in 2016 and used again in subsequent publications. It uses rules, as introduced earlier, for a finite set of field types like method lengths, sequence counters, identifiers, and addresses, for which it needs a rule for each of those field types. This rule set based approach limits the coverage to only 3% of the message bytes, because those kinds of fields are relatively rare compared to the amount of bytes in the messages. Thus, we can analyze almost all of the message contents. For future work, we envision that subsequent analysis of clusters can be used to identify the semantic function of the segments that are contained in the cluster. One possibility to perform this is intra or intermessage semantics that we can derive from statistics, and this is similar to what Field Hunter performs for message length, sequence counters, identifiers. And our hope is that we can combine the benefits of both approaches to raise the coverage and, on the other hand, identify concrete data types and not only pseudo data types. And finally, we think that visual analytics can be helpful for protocol reverse engineering, as we have seen with the annotated message bytes. There, the labels with the clusters help to identify structures, which can be useful for an analyst. And in topology plots, we could observe that there are specific shapes of clusters that can indicate data types. For example, linearly chained clusters indicate sequence counters. And there may be other rules that help indicate what data types are contained in clusters. To conclude my talk, I introduced the clustering approach for field data types in the context of semantic interpretation, which is part of protocol reverse engineering. Our method does not rely on a finite set of heuristic rules, and therefore we can raise the coverage of the bytes throughout traces from 3% to 87% that we can cluster correctly. Our method of an efficient auto-configuration makes it possible that there is no human intervention needed for any of the process steps, and therefore we also have no manual parameter selection for an undocumented protocol, which is tedious. And to give an example where this kind of protocol reverse engineering is beneficial, we published in last year's Historics the study of the Apple Remote Invocation Protocol, where we fuzz tested the protocol based on information we gained from protocol reverse engineering. Thank you for your attention and your interest in our work. If you have questions, feel free to contact me. The source code of our proof of concept implementation is available on GitHub, as you see the link on the right-hand side. And as a final note, my employer, Mercedes-Benz Tech Innovation, is hiring. And if you're interested in a career in security and starting a job in Europe, then please check out our career portal.